So let me start the recording. Okay, so I'm going to go over milestone 4 today. And, whoops, got a strange, I think I'm going to go over milestone 4. Let's see if I can make the slides advance. Okay, there we go. Okay, so milestone 4 is a different problem. So let me define what the problem is. Still in a city map, but you're optimizing the delivery route for a courier company. So courier company's got a lot of packages to deliver, and they're trying to do it in as little delivery time as possible. So the problem starts with these depots. So the courier company has got multiple trucks. They're stored in depots, parking lots. And this particular courier company has got 3 different parking lots. And they have to get a truck from, driver's got to go to one of these depots, but he or she can pick which one to start at. And then the driver has a bunch of deliveries to make. So I'm showing deliveries as, there are 2 pieces. There's a pick up a package and there's drop off a package. So for example, we have to pick up package A. So I'm showing a green A with an up arrow, and I have to drop off package A. So I'm showing a down arrow of blue A. And I've got another pickup, whoops, that's a drop off, sorry. I've got another pickup of, I got to pick up package B, and I got to drop it off down here. And so on. So in the problem I'm showing you, you've got 4 deliveries to make, and you can start your delivery day from one of 4 depots. So let me erase this. And you can decide what order you want to do this in. Okay, so we give you n deliveries, in this case 4 deliveries. They're all intersections. And a delivery, again, is a pickup intersection, a drop-off intersection, and a package weight, because your truck actually has a weight capacity too. So you might not always be able to pick everything up and carry it around to all the drop-offs. You might have to get some things off the truck before you can pick more things up. We also have M of these courier depots. In this case, M equals 3. And those are basically spots where you can get the delivery truck. So you start your delivery day, and spots where you can leave the delivery truck when you're done. And the truck has a capacity C, so it can carry a certain amount of weight. And that's important because your packages have different weights and they can't add up to, what you have on the truck at any point in time can't add up to more than its weight capacity. Okay, so what you have to, so that's your input. You get all of those things as inputs, and EC297 exercise has a bunch of unit tests, so it's going to send these into your courier function to return a solution. So what do you have to return? So you have to return a legal path. So a legal path starts and ends in some depot. So maybe I'll pick up the truck there, and maybe I'll drop it off here. We have to go through all n of these. We have to make all of these deliveries. So we have to go to all the pickup intersections, and we have to go to all the drop-off intersections. And the order matters. We can't drop off a package before we have picked it up, and we can't overload the truck. And the header file describes this in detail. You go, well, what are all those outputs? The header file is very heavily annotated, describing exactly what the data structure you have to return is. Okay, so here's a possible solution. So what this says is I picked up my truck at this depot. I went through this intersection, which is a drop off for B. Then I picked up D. Then I went over here. So I'm following along here. I dropped off A, picked up C, picked up B, and so on. Dropped off D, and eventually went out here, dropped off C, and then I came down here and picked up A, and finally I have to drop off my truck. Okay, so there's my solution. Okay, so here's your first chance. You've been waiting to unmute yourself or to chat. Is this a legal solution? Will you get any marks for this at all? What do you think?
Zachary is saying shouldn't be picked up before being dropped off.
Right. So this is the problem with basically, let's see if I can successfully change my pen color. So we're picking up B right there, and then we're going through a whole bunch of intersections, or we're dropping off B here, and then eventually we pick it up here. Okay, but that's much later. We go through this whole path and we get there. So that doesn't make any sense. Okay, we showed up at somebody's door, rang their doorbell, and said, there's a package that's coming to you, and I'm going to go pick it up later today. That doesn't make any sense, so that's not a legal delivery order. Now, you could have gone through that intersection. It's not like it's illegal for you to just drive through that intersection. It's just you can't say I dropped something off because you don't have it yet. So you're going to have to go back and go to this intersection again later. So that wouldn't have been a legal solution. We did start at a depot. We did end at a depot. That's good. We went through all the intersections, but the order we went through them, we wouldn't have made all the deliveries. I see there's another question, which is, can we keep only one thing on the truck? And no, you can keep multiple things on the truck. Every one of these pickups has a weight, and the truck has a certain capacity. So let's say every one of these, let's say these various 4 deliveries each had a weight of 30 pounds, and my truck had a capacity of 2,000. Then I could pick them all up, keep them all in the truck. I don't have to worry about it at all. But if each of these was some giant exercise gym that weighs 2,000 pounds, and my truck had a capacity of only 3,000 pounds, so it's a small truck, then I could only have one on at any point in time. So you have to check for that as well. Any other questions? All right, so that's not legal. So the most basic tests we have are legality checks. Did you get us a legal solution? And you would actually fail that check with this. It would give you a message saying you didn't actually make all the deliveries. Okay, so let's do a legal solutions. This one's a bit better. Let's see. Let's trace through what has happened here. We started at this depot. We went and picked up package D1. We dropped off package D1. We went and picked up package B1, or sorry, B, sorry, not one, those are arrows. Picked up package C, so we've got 2 things on the truck now, both packages B and C. And then we went all the way over here, dropped off C, and came back here, picked up A, came along here, dropped off B, came up here, dropped off A, and finally dropped our truck off at a depot again. So this is legal. We started in a depot, we ended on a depot, we went through all the intersections, and we did it in order where we actually could drop things off. Okay, so again, the m3.h header file tells you exactly what you have to return, but you basically have to return a vector of courier paths. Now, what's a courier path? The courier path is very similar to the output of your find path between intersections function from M3. At the start intersection, an end intersection, what deliveries you wanted to pick up at the start, because in some cases you might go through an intersection and because your truck's full or nearly full, you might choose not to pick something up. So we have you explicitly tell us, I want to pick this delivery up. And then a vector of street segments in between.
And some intersections might have multiple things to pick up at.
Yeah, so that's a good point. So some intersections also might have multiple things to pick up. I'll turn the volume off on this. So you might not be able to pick them all up. Maybe the truck doesn't have enough capacity. So to handle that case, you tell us, what am I picking up when I go through this intersection? Okay, so again, what you're returning is it's a vector, and every element in that vector is a data structure, which includes multiple things. So it has a start intersection, it has an end intersection, it has, in this case, we would say there's one thing we're picking up. We're picking up item A, and it has a vector inside of it. And that vector inside of it is the list of street segments that we followed to go from this start intersection, which was our A pickup, to this start intersection or end intersection, which is our B drop off. And again, that path is the same format as we used in the find path function from M3. When you're dropping something off, so at this end intersection, we know our next element in this vector of courier paths would go here. So it goes from B, in this case, to the drop off for A. Okay, that particular entry in that vector is not going to have anything to pick up at the start, and that's fine. Okay, so you would say I'm not picking anything up. The reason I went through that intersection was because I wanted to drop something off. Does that make sense? And again, it's very well commented in the m3.h. So if you didn't get every detail of that, like, don't worry about it. It's hard to describe every detail of code in words. Okay, so what's a simple solution we could use? So it's always good to get something going early and then gradually work to make it better. So it reduces stress, gives you a fallback plan. So that's agile development. Get something going and gradually improve it. So simple solution would be to use this milestone4 pathfinder. I already have a function that knows how to go from one intersection to another. So use that function again. Okay, so I'm going to start it off. We'll see if anybody can come up with a simple solution for this. But we could take, we're told there are several depots we could start at. There are M of them. Let's just pick the first one and go from there to the very first package, where we're given N packages to pick up and drop off. I'm going to go from the first depot that is a possibility to the very first package, and I'm going to invoke my find path to find the path between them. Well, so maybe I'll just go give you this one. Maybe it'll be too hard to do remotely. Okay, so I'm going to call my find path function, and you're given, again, a vector of depots. So I'm just going to pick the first one arbitrarily. I'm not trying to optimize at all. And I'm going to go to the first pickup. So I'm not trying to optimize the order at all. I'm doing this the simplest way I can. And I already have this find path function that knows how to find the street segments between the shortest street segment path, actually, in between two intersections. So it's actually going to figure out how should I drive between those two things. So that sounds great. Okay, now what I'm going to do is my simple algorithm, still not worrying about optimization. I'm just going to complete the deliveries in the order they were given to me. Okay, so I was given N deliveries to make. So, and they're given to me, if you look into the header file, as a vector of deliveries. So I'm just going to go through from delivery 0 to delivery N-1. And I'm going to say, well, I have this package on my truck. I need to drop it off. So go from where I was, where I just picked it up, to where I'm going to drop it off. And I need to find the path. So I call my find path function again. Okay, and now I need to go on to the next. I need to go pick something else up. So what I'm going to do is I'm going to say, okay, I just dropped off package I. Go to the pickup for package I plus 1. So I do another find path, and then I just loop over this. Okay, so I'm going to loop over this N times to make all of my deliveries. Okay, when I'm done, I still have one package left on the truck. So I picked up the last package here. I haven't dropped it off. So I do one more find path saying go from the pickup of that delivery to the drop off. And then I finally need to drop off the truck at some depot, leave it there for the night. It's too big, I'm not taking it home. And I'm not going to apply any intelligence here either. I'm just going to say I picked it up at the first depot. So depot 0, you know, there might be multiple choices. I'm not even going to look at the other choices. I'm just going to say I just dropped off my last delivery, and now I want to take the truck and leave it in the first depot you told me about. So let's call find path on that. Okay, so does everybody understand that? Any questions on that algorithm, or is it pretty clear how that would produce a legal solution? Okay, so I'm going to take that as it looks good. Okay, so let's draw what that would be for a simple test case. So I said I'm going to start in the very first depot. Okay, so this is the very first depot I was given, depot 0. And I said from depot 0, I want to go to the very first pickup. So let's say the alphabetical order that I've used here corresponds to the order of these pickups and drop-offs in the vector you're given. So I'm just going to go straight to A. So I'll go there, and I'm going to drop off pick up a package at A. And then I immediately drop it off. So I look at where is A supposed to go to? It's supposed to go over here. So I drive back and drop it off. So this doesn't look super efficient. I picked my truck up somewhere in Mississauga. I drove all the way across Toronto. I picked up a package, and then I drove all the way back to Etobicoke or Mississauga and dropped it off. The next thing I do is my next pickup was B. Okay, that's in the order that I would have been given these various pickups and drop-offs. So I go, I pick it up, and I'm going to immediately drop it off. So B is going down to here, And then I pick up my next package, which is C, and I immediately drop it off, which is way out in the edge of Scarborough. And then I need to go pick up D. All right, D is way back here. And then I go drop it off. And now finally I have to drop my truck in a depot, so I'm gonna go back to this first depot that I got the truck at, even though there's another depot that's closer. Okay, so what do you think? Is this a good solution? It is legal, so this will actually pass our legality checks. But we don't want you to just get a legal solution. We also are checking what is the total travel time. So we're gonna rank solutions or compare their quality to various reference solutions we have and see how good is the travel time. Okay, so I see someone is asking, can we get any marks in M4 if we do this? And yes, you will get marks in M4 for doing this because you actually have found a legal solution, but you won't get a great mark. So not this lecture, but next lecture, I'll show you a leaderboard where every time you submit your solution for milestone 4, your quality, so your travel time on a bunch of test cases will be computed and inserted into this leaderboard. It'll be anonymized, so you know who you are, but the other entries, you won't know who they are. It's just other students. And there are several reference solutions that we're putting in there too that we made. So this is actually one of the reference solutions, like a very simple, just I'm not optimizing the order at all. You won't pass milestone 4 with this, but you will get some marks. If you did this and you always got a legal solution for every problem that we gave you and you didn't fail any corner cases, you'll get probably something like 40%. So not a great mark, but you will get some marks. Any other questions like that? Okay, but that's actually a reason why it's good to get something like this going, because with an algorithm, it's not that complicated. You already kind of lock in some marks. I don't want to focus too much on marks, but this is actually a good engineering practice of you're de-risking a project. You have a solution, you're trying to improve it. If you run out of time, it's much better to have something working rather than I was going for something really elaborated and nothing works. Okay, so this works, but its travel time is pretty bad. And I showed you this with 4 deliveries. If I actually give you a bigger problem with maybe 100 deliveries, I mean, you'll be crisscrossing the city a huge number of times. You'll be spending far, far more time driving than you need to. So it's not a great solution. Okay, so a more logical solution. So a more logical solution, they exist for this. So I could have picked up my truck here at this depot and I can go to something that's close by. Package D is actually pretty close by, so I can go pick it up, then I can go drop it off. Then from this location, package B is actually pretty close, so I'll go pick it up. Package C's pickup is close, so I'll pick it up as well on the way. And now I can go drop off C, drop off A, or no, pick up A, because I'm actually pretty close to the pickup for A, so I'm going to pick it up. And then I can go back and drop off B and drop off A and go to a different depot. And this solution is already a lot less travel than the one that I just showed you. Okay, so we need to optimize the delivery order. So how are we going to do that? So in milestone 3, you're using algorithms, Dijkstra, A*, that are guaranteed to get the best answer. Okay, so you're using what are called optimal algorithms. They get the best answer. So maybe we can come up with an optimal answer for this problem too. And it's going to get us the best delivery order, and we search for that. Okay, it's not obvious what that algorithm would be. So let's check, well, maybe we just check everything. There's a finite number of delivery orders. Maybe we'll just check them all. So let's check, is that feasible? So how many combinations would we have? Actually, let me give you like 30 seconds, think about that. So we have N deliveries to make, so N things to pick up and N things to drop off, and we have M depots that are our start points. So we can start at one of M different depots. So how many different ways could we order that? Some of them are going to be illegal, but don't worry about that. Usually the way to handle illegality in something like this is you just check. So we want to know how many ways could we try to deliver these things. Some are legal, some are illegal, but we could write code that just checks, is this order legal? And if it is, what is the total travel time? Okay, So I see one person has said maybe it's n times n, so n squared. So I'm going to give you 30 seconds to think about this. If anybody else has got different ideas, either unmute and say it or just type it in the chat box.
Maybe n times m.
N times m, because I'm going to write down a few options. Okay, so we got a one n. I'm going to change back to red. I think I like red better as a color. Okay, so maybe we've got n squared is one option. I've heard n squared times m. Okay, probably makes sense that the number of depots comes into this as well. Let's see. Anybody else want to take a shot at this? With your last. Oh, I see another one. Okay, so I see someone says n factorial times. So Andrew says n factorial times m. Okay. Andrew, I don't know if you're on the line. Do you want to say how you arrived at that? Well, I guess I know you're on the line. I don't know if you're willing to unmute. Sorry, let me rephrase that. So it's your call. If you want, you can explain why do you think that. Okay, so, and I can see it in the chat window. So Andrew is saying, choose the first node. So we've got one of n choices. Then you have n minus one choices for the second node, like the second thing you do, because you've already gone to make the first pickup. Then continue that, you'll get n factorial. And then at the and then you also have m choices of how to start. So yeah, that is basically right. So I've got m truck depots. I've got n deliveries. Now, n deliveries mean I actually have 2n pickup and drop off locations. Like every delivery has a pickup and a drop off. So I've actually got 2n intersections. So first choice I make is which depot. So I can choose one of m things. Then I've got 2n choices, a bunch of which are illegal. So it turns out only the pickup ones would be legal. But let's say my code's not that smart. I'm just going to try all 2n of those things and then check legality afterwards. So I got 2n different things I could do. After that, I've got 2n minus 1 things I could do for the second intersection. I could try to pick something else up, or I could try to drop off, and so on. You might write code that's a little more clever than this, where you understand it doesn't make sense to try picking something up or dropping something off if you haven't picked it up yet. So maybe if you wrote more clever code, you could get it down to n factorial times m, which is what Andrew said. With my code that's a little dumber, it's going to be a bit higher. I'm going to have 2n factorial. At the very end, I have to drop off at the closest depot. And that one, there's really no decision. I could actually just at the very end see which depot am I closest to, and I could say I'll go to that one. So I don't actually have to try all possible depots. Just at the very end, I'm going to quickly check all m of them and choose the closest. So if I write all that out, I do get m times 2n factorial. And as I said, if you were able to write sufficiently clever code, maybe you could get this down to n factorial times m. But my code's easier to write. Okay, because yeah, some of these are illegal, and I'm just checking them after the fact. But it's a lot. So let's see, is this too much? Computers are pretty fast. Maybe it's okay. Okay, so Abid, what's the biggest problem that we're going to give them in this? You just created the test cases. What's the biggest one?
200 or 250, something like that.
So n equals 250.
Yeah.
Okay, so they're even bigger than what I've
people.
listed here. So we've got 10 depots, and 100 pickups, 100 drop-offs. Okay, let's just walk through that math though. So if I use that formula, m times 2n factorial, that's a really big number. It actually starts, you have to go get a calculator that can, I'd actually approximate this. It's hard to type this number into a calculator and get an answer. So it's about 10 to the 377th, okay? So computers are pretty fast. Abid, what do you think? Are computers fast enough? Is it still gonna be okay?
Definitely not.
No, so computers are nowhere near this fast. So let's put this in context. Let's say that I'm also, every time I come up with a possible ordering, I'm going to invoke find path between all of those intersections in the right order to figure out what's the travel time. Okay, so tell me how to get between all these things, tell me the travel time, add it all up, and now I know the time for that order. I can say whether it's better or worse than what I found before. If I do that, your find path, if you've got a pretty fast implementation, it takes about 1/10 of a second. And that's a pretty good implementation. and I have to invoke it again 2n plus 1 times for every one of these delivery orders. So I multiply all that together. The big number is 10 to the 377th possibilities times 201 invocations of my find path times 1/10 of a second each. I get a really big number. I get 10 to the 378 seconds. Does anybody know how long the universe has been in existence? Kind of a hard question, I guess. Okay, I know this because I looked it up. Okay, that is 10 to the 370th years. And the lifetime of the universe is estimated to be 14 times 10 to the 9th. So this number is like vastly, hugely bigger than the lifetime of the universe. So, so no extension that you could request could possibly, or relaxation of the timeouts that we have for milestone 4 would possibly let you pass this. So this algorithm is not possible. We cannot use an exhaustive algorithm. It's way, way, way too slow for the size of problems that we're giving you. And I see someone has asked the question in chat of, will there be a performance requirement for M4? Yes, every one of the problems we give you, including this biggest one, 250 pickups and deliveries, you have to return an answer in 45 seconds, okay? So if you try, this clearly you will never return an answer, you will simply fail that test. So there's kind of two things you're doing for M4. Give us a legal answer for every question, like every test case we give you. And then within that 45-second time limit, try to make it as good as you can, meaning smallest travel time. But you want to get both. Not giving any answer is bad, worse than anything. And then within that limit, make it as good as you can. Okay, so we can't do this. So, okay, so there's another question of, what if I fail the performance test? Will you be given credit if the corresponding functionality test is passed? At 45 seconds, we just consider it a fail. So you have to return an answer in less than 45 seconds for every test case. If you return it in less than 45 seconds, we check its legality. So it has to be both legal and less than 45 seconds. And then if it passes both those things, then we check what is the travel time, and that'll affect, do we think it's a good, bad, so-so, whatever solution. But the first set of marks are just return us anything that is legal within that 45 seconds. Okay, so we're solving a variation of a very famous problem called the traveling salesman problem, which is basically try to find a good order to go between a bunch of nodes in a graph or cities on a map. This is called a computationally hard problem. So computationally hard problem means there's no guaranteed optimal solution in polynomial time. Okay, so optimal for us would mean lowest travel time, like the best you can get, nothing is better. And polynomial time, what polynomial time means that the order of the algorithm is, well, if it's not polynomial time, then the compute order of the algorithm is greater than n to the k, where n is the number of intersections we're considering, number of deliveries. For any k we can choose. So it's more than n squared, it's more than n cubed, it's more than n to the 256th. For some sufficiently big n, there is no constant k. So even n to the 10,000th would not be enough. It's even slower than that. What that means in practice is that the algorithm is at least exponential. So it's ordered 2 to the n. And 2 to the n exponential grows really fast, because you just saw for the 100 intersection case that we wound up with, compute times that were longer than a lifetime of the universe. So can't do it. So we have to use heuristics to solve. Heuristic just means good idea. It means I can't prove this is going to work. Probably it just doesn't give a great answer all the time, but it seems like a good idea. It seems to give a good answer most of the time, so I'm going to use it. So there are smart heuristics, there are less smart heuristics. You're trying to come up with some smart ones. Okay? Most research problems where you are trying to come up with new algorithms are computationally hard. So you want to know optimal algorithms. You just learned Dijkstra's algorithm, you learned A star, or maybe you're still in the process of learning those. Those are important optimal algorithms, guaranteed to give the best answer. But most research problems, they'll often use those algorithms as building blocks, but the overall thing you're trying to solve is harder. It's computationally hard, meaning there's no perfect solution. So in integrated circuit design, where I've done a lot of work, the most of the problems are computationally hard. You can't get perfect answers of how to put these things on a chip. You have to come up with heuristics to try to do a pretty good job. Same thing for drug design. There are big simulations that people do about how molecules will interact and therefore what might be a good drug. And those are also computationally hard. Can't perfectly do them. Transportation network design. So that's very close to what you're doing in this course. So if you're trying to build a road network to minimize congestion or to be as low cost as possible and still get people where they need to go, that's computationally hard. No perfect answers. So it's really good to gain experience in how to attack these. And it requires a lot of creativity, actually. The fun thing about those algorithms is because there are no perfect answers, everybody comes up with their own ideas, and it's quite a creative exercise. I enjoy it, and hopefully you will too. Okay, so there's a very famous professor at U of T named Stephen Cook. He's a professor in computer science. On the chat or with your hand, who has heard of Stephen Cook? Who knows who Stephen Cook is? Okay, Abid, you don't know either?
No, I know.
Okay, so it's good to have you on the line. Okay.
Yeah.
Okay, I see a couple of people, 3 people at least are saying they know, and 1 person for sure knows because he's actually pointed out an important item from Dr. Cook's past. All right, so at least 4 people know who Stephen Cook is. So for others who are too shy to jump in, I'm gonna tell you a bit about him. Okay, so he came up with basically the theory of what are called NP-complete problems, which I just gave you a kind of an informal definition of. So basically an NP-complete problem means not polynomial. So no polynomial time solution is known on conventional computers. So those are the kind of computers that we use today, not quantum computers, regular computers. And no polynomial time solution means for a problem of size n, there is nothing of order n to any k, not even n to the 10,000, not even n to the million, that bounds the compute time if n is big enough. So it means it's got to be at least exponential. Okay, so what did he prove? He proved that if there's a method to solve any one of these large number of problems, I just talked about drug design and computer chip design, and there are many other ones that are in this NP-complete class. If you ever find an algorithm to solve any one of them in polynomial time, meaning order n to something, n to the 3rd, n to the 10,000 something, then all of those problems can be solved in polynomial time because they can all be mapped they can be mapped to each other. That mapping is sometimes very complicated, but it would actually allow you to solve them all in polynomial time, so far more efficiently with a perfect solution than is currently known. Okay, this is actually the most famous open problem in computer science. So he proved that if you can solve any one of these NP-complete problems, you can now solve all of them in polynomial time. But he was not able to show that a polynomial time solution exists or doesn't exist. So clearly no one's ever found one. So we don't know of any polynomial time solution, but no one's ever been able to prove that it doesn't exist either. So that's called P versus NP. If somebody ever finds an algorithm that's polynomial time for one of these problems, then they just basically proved that all these problems that are believed to be intractable to get perfect solutions for, that in fact you can. So if you're actually a risk taker, you could say, I'm going to try to work on this. I'm going to prove P equals NP, or P is, like, I'm going to prove that either that algorithm exists or that it cannot possibly exist. And if you do, you will actually win a Turing Award, I'm pretty sure. But probably nobody's been able to prove this. So it's a really challenging problem if you decide I want to be the one to prove that either there is no algorithm or I'm going to find the algorithm. Okay, so interesting story about Stephen Cook, though. In 1970, he was denied tenure at UC Berkeley. So he finished his PhD, became a professor at Berkeley. None of you have ever gone through the tenure process, but it's kind of a bizarre thing, actually. You work like crazy to get your PhD. It takes you maybe 10 years to go through all your education. Then you become a professor. You work really hard for like 6 years, publishing papers and so on. And you write up all your life's achievements, and a group of people at that university and around the world say you should either be given a job for life or you should be fired. So it's actually quite a stressful thing. For 6 years, you just work away, and then a group of people are going to judge you as worthy or not. And he was denied tenure, which is usually a pretty, it's not a happy thing, right? You just spent 6 years of your life and you now just got to go on to something else. You were really hoping to get tenure, obviously. And he came to U of T after not getting tenure. So, this is not the end of the world, but it probably wasn't a happy day for him to not get tenure. But U of T said, we think your work's good, come here. So he came to U of T. In 1971, he published this P versus NP paper, his most famous paper. In 1982, he won the Turing Award, so the computer science version of the Nobel Prize for that work. And then Berkeley called him up to say, if you would like to come back, we'd be very, very happy to give you tenure now. But I don't know exactly how he expressed he did not accept that offer. I think this is, the reason I know about this is considered one of the sort of biggest tenure committee fails ever. Like that Berkeley had somebody who was going to win the Turing Award and they denied him tenure. And then, yes, they offered it to him later, but he was no longer interested. And someone is asking, does U of T have tenure? Yeah, U of T does have tenure. Stephen Cook definitely has tenure at U of T. U of T is never going to let him go back to Berkeley if they can avoid it. So anyway, so it's an interesting story of basically resilience too. So things happen even to people who have incredibly successful careers. They have setbacks, and this is a much more emotional setback than failing a course or something like that. This is something where you would feel like I've just failed the last six years of my life. Clearly, he didn't let it get him down too much, and the university that made that decision came to regret it and be held up as an example of tenure decisions gone horribly wrong. So all of us are going to have setbacks in our lives, and it's useful to see some people who handled them really well. Okay, so you're not going to solve this perfectly, though, is the takeaway from that. So let's talk about heuristics. We've got basically a very naive algorithm that gets us a legal solution, and we've got an exhaustive algorithm that's not reasonable, so we need to come up with heuristics. Okay, so any ideas for this? Why don't you so I showed you what if we just connect things in the order that we're given, and it's not great, but it gets us a solution. What can we do that's better, that's not very complicated? So maybe just on the chat line or unmute yourself, just weigh in if you got an idea. What's a better delivery order than what we just did of just connecting them in the exact order we were given? Okay, I see we have, let's see if I can. Okay, so I'm gonna unmute Annie, because I see you've got an idea. Do you want to share it with the class? So Annie, I've just unmuted you. Do you want to tell us what you think? Or would you like me to remute you? So I can't hear you. I'm not sure if your mic is working or not. Okay, I see you typing things in. So could you look for the nearest pickup from there? Okay. And actually, I see another person has a similar idea. So Andrew's also saying traverse the graph by going to the nearest point always. So I think you both have a similar idea. So that's a good idea. And Annie's saying look for the nearest drop-off point or look for close by other pickup. So both of you, I think, are saying similar things of let's look for things that are nearby where we are. Okay, so let me try that. Whoops, let's see if this works here. Okay. I bring my cursor back. Let's see if that'll work now. Oh, okay. All right, so I'm going to write out basically what you guys have written in the chat. So let's go from any depot. So we can start at any depot we want, and let's just check for all those depots, what's the nearest pickup? We know we have to pick something up first, so let's go from there. From every depot, let's check what the nearest pickup is. Whichever one of those gives us the smallest travel time, we can call find path to find that out. We're going to start at that depot and go to that pickup. Okay. And then we're going to have to go through all of our other pickups and deliveries. So we've got a package on the truck. We just picked it up. Let's drop that off. So we're going to go to the drop off point, and then we're going to say, let's go to the nearest remaining pickup. Okay, so we'll check all the other pickups that are left, which one's closest in terms of travel time. Let's go there and pick up the next package. And then we're going to repeat. Okay, so we're going to drop that package off, and then we're going to say, well, what's the next remaining pickup? Okay, at the very end, we have to drop the truck off. We'll just check all the depots, see which one we're closest to, and go drop it off there. Okay, so let's look at what the complexity of this is. So we need to go from any depot to the nearest pickup. So we want to figure out what's the best choice there. So there are M depots and there are N pickups. So there are order N times M choices. So we're going to check them all, pick whichever one has the lowest travel time. We get to this loop. When we go through this loop, we'll go through it N times. We have N pickups and drop-offs to do. And inside the loop, this line says, go to the nearest remaining pickup. So that's order N, right? We have N things that we could choose from to pick up, pick the one that's closest, and let's go pick up a package there. So that's an order N computation because we're going to check all of those possible pickup locations. So we got N here, we're going to go through N times, that's order N squared together. The very end, we go to the nearest depot. That just means checking M depots and seeing which one's closest. Okay, so what's the overall complexity? So we just add it all up. M times M plus N times N squared plus order M. We take out whatever's the biggest. So biggest is M times N plus N squared. Usually this N squared is going to be bigger because we give you more pickups and drop-offs than we give you depots. But if we ever gave you a case where M was really big, this term might be bigger. But it's basically an N squared algorithm, which is hugely better than the exponential one when we try to do exhaustive search. Okay, so let's quickly check, is this fast enough? Okay, so it's much better. So it's order M times N plus N squared. So let's say we have 10 depots and we have 100 pickups and drop-offs, which is close to the biggest problem we'll give you, although as Abid said, we're going to give you a little bigger. 250 is the biggest value we'll give you for N. Okay, so what's our time? Our time, we basically say it's some constant times this order. So it's a constant times, and I just plug in the numbers for M and N, and I get a constant times 11,000. Okay, so what is this constant? Let's say that for every one of these possibilities, we're going to call that find path function. So find path between two intersections that you just wrote for M3. I told you earlier that for a pretty good implementation of that, it'll take about 1/10 of a second in most of the street graphs we've given you. If I multiply this through, that's 1100 seconds. So it's a lot better than our lifetime of the universe, but it's still too big because we're going to only give you 45 seconds. Okay, so that's greater than our 45-second time limit. So you're going to do better. Okay, so any ideas? Can we do better than this? I like this basic algorithm, and it seems like it's not doing a ridiculous amount of work, but this find path is hurting us, right? The fact that it takes 1/10 of a second to find the paths. And someone is asking, or Kelly is saying, do we need to call it all possible pickups? Can't we just call find path once? So that's a good idea. I mean, find path is what's killing us here. We're calling find path right now a lot of times to sort of evaluate options, like what is the nearest pickup? So I'm at a certain intersection, I want to know what's the nearest pickup. I basically am calling find path to all the remaining packages that I could pick up. And then I'm going to just look at the travel time. That's actually all I want is the travel time because I'm going to choose one of them. And so the question is, do we have to call it so much? So Kelly, I don't know if we want to unmute yourself or just want to go on chat. So you're saying, should we get the closest one first? Okay, so there's actually two. Kelly's got some very good ideas here. Okay, so basic answer is, yeah, we don't have to call find path so much. So let me show you the simple way to call find path less. And then Kelly's actually hinting at a better way still, which I'm going to get to in another lecture. So simple way we can call find path less is we're just going to estimate our travel time as geometric distance. Okay? If we do that, that can be done really fast. So 10 to the negative seconds at most. It's pretty fast. It's only a few operations. If I take 10 to the negative 7th as my constant in this equation up here, and I multiply by 11,000 computations, it's less than a millisecond. So this algorithm now is extremely fast to choose the order. I still need to actually construct the paths at the end. So I still will need to call find path once I've chosen an order, but now that's only 200 calls. I actually know what the order of intersections is. I just have to call find path to go from this pickup to this drop off, then from that drop off to this pickup, etc. If n equals 100 pickups and drop offs, that's about 200 calls. which if each one takes 1/10 of a second, that's 20 seconds. So that's going to work, right? That'll fit in our 45-second time limit. So now we've got an algorithm that's much better than random. And it also, if our find path from milestone 3 works, it's also going to come in under this 45-second time limit. Does it make sense? Okay, now one last comment on Kelly's comment. So Kelly is pointing out something that I'm going to get to again in a lecture or so. Using geometric distance has some cost. It's not perfect. It's an estimate of the time to go between two intersections. So it might hurt our quality. Sometimes we might choose to go to a certain pickup and it's not really the one that's fastest to get to. It's geometrically closer, but maybe another one's close to the freeway. We could have gotten to it faster. So this may hurt our quality some, but it is fast. It's easy to compute. By leveraging some of the things we talked about yesterday in pathfinding, there are ways that we could use Dijkstra's algorithm to get a lot of fast paths in one call. So there are ways to get the perfect travel times with much fewer calls than what I've shown above. And we'll get to that in about a lecture. But for now, we're going to say, let's just use geometric distance, which you compute very quickly as our estimate of travel time. Once we got an order of deliveries, then we'll just fill in the paths by calling find path. Okay, so let's look at how this algorithm works. So here's my little 4 delivery example that I've been using. So we are going to look at all of the depots. So the first thing we do, we look at all 3 depots, here, 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 and we say, which one of them is closest to some pickup? So from every depot, we check how far are you from every single pickup, and we pick whatever depot pickup combination gives us the minimum travel time. So let's say that's this one, okay, going from this depot to A. All right, now I basically, in the code I showed you, we say, okay, let's go make the drop off for A. So we're gonna go drop it off over there. Now we say, what's the next closest pickup from where I am now? So I'm here, and I can check all my remaining pickups. So I've got one here, I've got one here, I've got one here. I'm gonna check them for speed. I'm just gonna check them with geometric distance. This one is clearly the closest. I'm gonna go there, okay? And then the algorithm that we're using right now says, as soon as I pick something up, go drop it off. So I'm gonna go drop that off, and that happens to be way over here. Across the city is where that needs to go. Now from here, I check, okay, how close am I to my remaining drop-offs? And I've got my remaining pickups. So I've got 2 remaining ones there and there. This one is geometrically closer. Let's go there. Oops. I guess when I did this, I felt that was geometrically closer. So even though I don't think it is. So let's say I go there. Then I'm going to go drop that off. So the drop off is down here. And now I've only got 1 remaining pickup. So I'll go pick it up. And then I got to go drop it off. And now finally, I got to drop the truck off. I could drop it off at this depot, or this depot. I'm going to compute which one's closest, which is this one here. And I'm going to go drop it off. Okay, so the output of this algorithm is a lot better than what we had, what we had before, our naive algorithm. So it is improving things a lot. But you can see this truck driver still loves going back and forth on the 401, right? We crossed all the way across the city to get to the sea, and then we came all the way back. So maybe we can try to get rid of some of that. Okay, so any ideas of there are some pretty simple changes you could make to this code to make it a bit smarter, and it'll get a better answer. Okay, let's see. So one answer I see here from Andrew is, what if we visited all nodes within a certain radius and expand that radius outwards every time all nodes within that have been visited? Yes, that's a reasonable answer. Let's look at all the things close by, and maybe there are multiple things we could do. Annie is saying, before you drop off a cargo, look and see if there's a closer pickup. So don't consider just, if I go back a couple slides, you'll see, so those are both good ideas. I'm going to run with Annie's idea because it's a little easier to code. And I like coding easy things. So I always go with the simplest algorithm first. And for heuristics, sometimes actually surprisingly simple algorithms work very well. So I would strongly encourage you to try simple algorithms and then keep building in things and trying them, seeing if they make it better, rather than just trying to code up something really complicated. Sometimes complicated is not as good as you think. So yeah, if we look at this algorithm, we are using some intelligence when we choose our pickups. We're saying what's the nearest one, but we're not using any intelligence for our drop off. We pick up something and we immediately drop it off. We don't evaluate, maybe I should pick something else up. I got this mostly empty truck. Maybe I should go get another pickup before I do a drop off. So let me just skip through all this again. So that's a good idea. Let's try to give the algorithm a little more flexibility. Let's try to look for, should I immediately drop this thing off, or should I try to do another pickup? Okay, so the change for that is not very big. Still start at some depot, go to the closest pickup. We have to do that because we can't drop off before we pick up. While we have packages deliver, all I have to change is this. Go set my next point that I'm going to go to be the nearest legal pickup or drop off. So I might drop off the package that I have, but I'm also going to check, are there any other pickups where I have enough capacity to put them on the truck? Okay, I'm going to keep doing that until I've delivered all the packages, and then I'm going to drop my truck off at the nearest depot. All right, so let's check the complexity. Is this slower or not? This hasn't changed, order n times n. We're going to go through this loop 2n times instead of n times because I changed the loop structure. I'm going to check, there are n things that I'm going to, or order n things that I'm going to consider picking up. So n pickups and n drop-offs. So I'm considering a few more things, but it's still order n. And go to the nearest depot is still order m. So the overall complexity hasn't changed. It's still n squared plus m times n. I'm doing a little more work in this loop. So maybe I'm doing twice as many comparisons, but it should be fine. I haven't changed the order of the algorithm. So let's see on our little test case if this looks better. Okay, so we're going to start off at this depot and go to that pickup again. And then we're going to actually pick up the next closest thing. A is pretty far away. So that's the drop off of A. So we actually don't want to go there. We find there's a pickup that's closer. So we go and pick up this delivery D. Then we're actually pretty close to its drop off. So we'll drop it off right away. And then we check what to do next. We find this pickup for B is close. Then pickup for C is close. So we got a bunch of things on the truck now. We can next closest thing is we could drop off A. Then we could drop off B. And finally, we could go drop off C. Now, if you remember the previous solution, we've gotten rid of a lot of back and forth on the 401. So this looks a lot more optimized. We kind of start here and we're going through the city without a lot of detouring. You know, we go in kind of a big circle with not too much detouring. So it is actually a much more efficient path. And the code change was actually very small. Okay, well, then I have to drop it off drop my truck off at a depot, so I drop it off there. Okay, so both of our heuristics, so I call the heuristic 1 and heuristic 1++, so just a bit better version, are what are called greedy heuristics. So a greedy heuristic makes the next decision greedily. It makes the best decision you can make now without ever changing a decision. Okay, so it's like you deciding what is the very next thing you're going to eat, and you don't want to think about the future very much. Just what are you hungry for right now? Okay, that's why it's called greedy. So greedy algorithms are generally fast, which is good. They often don't get the best solution, but sometimes they can. Dijkstra's algorithm is actually greedy, but because it makes the decisions in a very specific order, it sorts things on the wavefront, so it makes decisions in a nice order. It actually gets the best answer. But for traveling salesmen, it's more complicated. You don't get the best answer with a greedy algorithm. So you can make smarter variants. Our greedy algorithm kind of just looks at what is the very next thing I'm going to do? What's the closest thing I could pick up or drop off? You can make them a bit smarter by having them try to predict the future. What will happen after that? If I go pick this thing up, am I in the wrong part of the city or not? And that can make your greedy algorithms a bit smarter, but still pretty fast. So these are a powerful class of algorithms, fast, usually don't get the best solution, and they won't get the best solution for this problem, but they can get pretty reasonable solutions, and they can be made even smarter if you have them do some predictions of what will happen. If I make this decision, what will happen afterwards. I don't need to truly know. I just have some guess of whether it's good or bad, and I can use that to influence whether I do it or not. Okay, so I think I'm going to stop there. So we'll keep talking about some additional techniques. We've got a bunch of different things we can layer on top of this. These greedy algorithms are a really good starting point. And then we're going to talk about various other algorithms we could bring in to improve their solutions. I think I'm going to leave off for there today. Are there any questions before anybody goes? Okay, and if anyone who does not have a question, you can basically just drop off the line. And when the last person drops off the line, I will stop the lecture. I'll talk to you next week.